the Cauchy theorem saying that at least in stated in your textbook, there are different textbooks state differently. So so this the Cauchy theorem is that if you're going through a loop and fc dz is 0 over a curve c equals 0, if c is within the c, no, get rid of all that. This path z is within a region, a larger region, that f is analytic over this. Okay, you have a function f that is analytic over a certain region. You can give it a label if you want, but within this region, any closed curve, closed loop of this function f is an analytic over this region. So over any closed curve within this region, this loop integration will be zero. Okay, so that's the Cauchy theorem. Okay, so at least you know how to state the statement. That's the statement of the theorem. Okay, that is important. Let's see where we. All right, so now we get to at least so-called proof that not a very rigorous proof, but we'll do it anyway because that illustrates something at least tied up to what we learned before. So last time we defined that derived the Cauchy-Riemann condition, and we'll use the Cauchy-Riemann condition to see why this is so. Okay, so that's now to do that now, not knowing that it's zero or not, so we just do what we said we would do, which is separate this integral in the real and imaginary part. So f is this one, dz is this one. We multiply the two together, so there will be real part and imaginary part. So the real part will be this times this, right? The u dx, right? And then this times that, but that will be there will be that you need a negative sign. I times I is minus 1, so v by minus v dy. So that's the real part. Okay, and then there will be an imaginary part. So it will be f times dy will be I here, loop over c, f, no, f, u dy, u dy, will give you I, and then v dx plus, there's a plus v, that will be your imaginary part. It's okay, so this, now that everything is back to familiar territory because u and v are function of real variable x and y, and these are just loop integration in the xy plane, and you learn about that in calculus, right? Hopefully, right? So supposedly that those are you can use your knowledge in doing loop integration and all that path integral that you learn from calculus to do that. And the textbook user actually used Stokes theorem to move on. You remember the Stokes theorem, right? Do you still remember? Yeah, your question? Yeah, this is when I wrote curious to illustrate the other point. So this C loop is defined as counterclockwise. So when we that's the convention when we write this symbol, meaning this loop integration is going counterclockwise. This is the convention. Okay. And if you actually evaluate in the clockwise direction, you get a negative sign. Okay, that's what I mentioned, that there's a convention in loop integration. Is that okay? So this is the path. The direction of the path is this one, whatever this Z is. Is that okay? All right. You can, I mean, if you follow your textbook, you see all these. Yeah, the Stokes theorem. You still remember Stokes theorem? Everyone who can remember the Stokes theorem? Not really. I mean, supposedly the textbook use Stokes theorem is because, well, author might assume that you remember the Stokes theorem, so therefore he used Stokes theorem. And let's just try it out and see if you kind of remember that. Here, Stokes theorem is, you can start either way, either, so in many cases, we start with the curl, and I'm writing it as a vector B because we usually apply that to magnetic field. Yeah, so we can do that, and this is a curl of a vector field. It doesn't have to be real field or magnetic field. And then this is going through a area integration, so dot into the area, but this area is enclosed by C, and unlike the complex area with this C, this curve can be more general than this. This curve is on the XY plane, so it's on a plane, but the structure of this C can be in a three-dimensional space. It can be twisted in the three-dimensional space, but that doesn't matter. So we have a curve C. Doesn't have to be on the loop. It can go outside, inside. But you define an area according to the right-hand rule. So dA is so there will be an area or surface. This surface can also be curved. So and you define the right-hand rule. So if you go through this counterclockwise direction with your fingers, then the direction of the sum is the direction of the area. So the area going out is a dA. So this is a dA, and integrate over this surface, right? And that is equal to a loop integration of this is the area, I should say. This is an area, or surface integral. And this is a loop integral. So I see d dot dl. dl is going along this direction of the C. Along again is going through the counterclockwise direction by convention. So that's the structure. It's okay. Now you remember this. Now you can follow your textbook to apply that. So like your B now, B, because now all we have is this part, B dot DL. So like you consider this the second one, the imaginary part. So this will be this is a U. U will be your Y components of B. The B will be, you have the X component will be V, and the Y component will be U, right? Because this DL again is just, you have just dx in the X direction. This is in the XY plane. DL is X, dx in the X direction plus dy in the Y directions. So this dot and that will be this one, right? So now B is that now this dA for this situation is the third direction. So this is X, this is Y. The third direction usually we call it Z, but unfortunately we already use Z as a notation or complex number. So there's a confusion of notation. So whatever, or you can use this as a K direction. There's a K direction, right? IJK or again, I is already used as complex number, but Anyway, we just need this direction. This k direction is the a. The a is the k direction. And if you remember how to do curve, you still remember how to do a curve, this curl operation, right? If you don't remember, you can just these are unit vector, j, k, right? Partial x, partial y, partial z. This z is not the complex number z, but we actually don't need that because we only need the k component, and then this is dx, dy, dz. And we only have x and y. We don't actually have this one. But again, it doesn't matter because that the curve is just this operator and that in the k direction. The k direction is this one, and the minus this one, right? The partial y component partial x minus partial x component partial y. So curve B is the y component is u, so partial u partial x. This is in the k direct k component, right? K dot is partial u partial x, and then minus this, the x component is v, and partial y. Did I get it correct? Okay. Yeah, that's fine. Yeah. This is minus. This is minus partial v partial y. This is x is v. This is all right. That's fine. And then this is a is this one is dA is just dA is just dx dy in the k direction. Okay. And so well b dot dA is just this one times dx dy. So the second one, you can see that this is just equals to not considered I. It's just partial u partial x minus partial v partial y dx dy. And what is this? What should this be? Remember what we learned last time? Remember the Cauchy-Riemann condition? What is the Cauchy-Riemann condition? The two equations, right? Right? Yes. Zero, yeah. The two Cauchy-Riemann conditions, right? So partial u partial x equals to partial v partial y, partial u partial y, and there's a minus partial v partial x. Right? Remember that? So partial v partial y is equal to partial u partial x, so that is zero. So the imaginary part is directly zero. Okay, it's okay. So at least we know that imaginary part is zero. And so this is following your textbook. The textbook uses Stokes theorem, assuming you know Stokes theorem. Remember Stokes theorem better, but apparently maybe not. But instead of doing that, you actually this form, this equals to that, you can directly cite it as a green theorem. If you still remember your calculus, probably you go through that. This equation, this expression going to here is just exactly the green theorem, the statement of green theorem. And there are many green theorems. There's one of the green theorems. Okay, and the proof of this green theorem is pretty straightforward. Actually, might be easier to go through directly prove that these two are the same. Okay. You remember that? You know how you do that? How you derive that this green theorem in calculus? No. But I don't know if I have time to go into that. Uh, Probably not. So. But you can go back to your textbook, or you still have the textbook of your undergraduate calculus or something with the green theorem. So this statement is exactly the green theorem without using Stokes theorem. This is another theorem. You can directly use that. Just as valid, assuming you know the proof. Sorry, but anyway, just like the example. So, and usually, the calculus will prove the green theorem first, and then prove the Stokes theorem by using the green theorem. So, but the textbook doing it the other way around. But that's okay. So we are actually not doing a rigorous proof. So either way is fine. So just the logical flow is a little different. But anyway, we got the imaginary partial is zero. That then we can work out uh, the real part. And now, according to the same rule, what is this? Now, without going through all that, how do you write it out explicitly? What should it be? It should be something similar. What should this be? Say it again. Du dy, and then okay. How do you get it? You write just interchange, yeah, right. Because you can just because u and y are just what we call them, just give them a name. You can always call this u as your minus v, this v as your u, right? You change that, you call your u minus v, so this is minus v minus x, and you call your vu, you know, right? That, so this equals that. You can use exactly the same equation and then just substitute, just interchange your suitable variable, and that you get this one. And what is this one? Zero again because of this one, right? Partial v partial x is minus partial u partial y. This becomes partial u partial y, and minus that is also zero. Okay, so both real part and imaginary part are zero. So the total is zero because this is what we set out to prove.